Hello again, Math 200, on to section 1.3. So section 1.3 is about data collection and experimental design. Designing a statistical study. So the guidelines for designing a statistical study would be we want to identify something that we're interested in and the population that would be involved in that interest. Develop a detailed plan for collecting data. If you use a sample, make sure the sample is representative of the population. Collect the data. Describe the data using descriptive statistics techniques. Remember, that's one part of statistics is descriptive statistics. But then the second part of statistics is inferential statistics. That's where you interpret the data, make decisions about the population using those inferential statistics techniques that we'll learn later. And then identify any possible errors. All right, here are two types of studies. One is an observational study, and the other one is an experimental study, or just called an experiment. In an observational study, a researcher observes and measures characteristics of interest of part of a population, but does not change the existing conditions. In an observational study, you are just observing something that is already there, something that already is. Whereas in an experiment, you are doing something to manipulate the data. You're doing something to cause some sort of an effect. You're giving a treatment. Let's read about it. In performing an experiment, a treatment is applied to a part of the population called a treatment group, and responses are observed. Another part of the population may be used as a control group in which no treatment is applied. The subjects in the treatment and control groups are called experimental units. In many cases, subjects in the control group are given a placebo. A placebo is a harmless fake treatment that is made to look like the real treatment so that neither group knows whether they're getting the actual treatment or not. So let me give you some examples here. So let's say you wanted to study concussions and their effects on memory or the ability to learn or whatever. Would that be an experiment or an observational study? That would be an observational study, not an experiment, because if it was an experiment, that means you have to go around giving people concussions to study that. No, we don't want to do that. We want to do an observational study, which is to study the people that already have had concussions at some point in their life to see what effects those things may have had. So in an experiment, you are giving a treatment. You're causing a difference between groups to study what effect that difference may have. So let's say you wanted to study the effect of, let's say, Love Potion number 9. Y'all might want to listen to that song at some point from back in the day. It was a pretty good movie too. So Love Potion number 9, you say you spray this on, you're going to get more dates. So you give, you get a control group, you get an experimental group. You spray Love Potion number 9 on the experimental group, and you spray some fake thing on the control group. You say, now go out and get some dates, and you try to see if Love Potion number 9 truly did have an effect on getting more dates for the experimental group than the control group. All right, let's go to this example. Researchers study the effect of vitamin D3 supplementation among patients with antibody deficiency or frequent respiratory tract infections. To perform the study, 70 patients received 4,000 IUs of vitamin D3 daily for a year. Another group of 70 patients received a placebo for 1 year. Is that an observational study or an experiment? That is an experiment because you, the researcher, are giving the supplement and the placebo. You're not observing something that's already happening. All right, number 2, researchers conduct a study to find the U.S. public approval rating of the U.S. president. To perform the study, researchers call 1,500 U.S. residents and ask them whether they approve or disapprove of the job being done by the president. So at that point, you're doing an observational study because you are not applying anything to them. You're not giving them a drug to make them think one thing or another. Hopefully, you're not giving them a loaded question to make them think one thing or another. So you're just observing what's already happening. All right, there are several ways to collect data. Often the focus of the study dictates the best way to collect the data. Here's a brief summary of the two methods of collection. A simulation is the use of a mathematical or physical process to reproduce the conditions of a situation or process. So it's like a computer simulation or something like that that simulates a process. You want to do that when there's danger involved, like like a plane crash, or how you react when something jumps out in front of you in the road or something. You want to do that using simulators of some sort, not putting that in a real life dangerous situation. The other way is a survey. A survey is an investigation of one or more characteristics of a population. Most often surveys are carried out on people by asking them questions. The most common type of surveys are done by interview, internet, phone, or mail. In designing a survey, it is important to word the questions so that they do not lead to biased results, which are not representative of a population. For instance, a survey is conducted on a sample of female physicians to determine whether the primary reason for their career choice is financial stability. In designing the survey, it would be acceptable to make a list of reasons and ask each individual in the sample to select his or her first choice. To select her first choice in that case. All right, experimental design. All right, 3 key elements of a well-designed experiment are control, randomization, and replication. All right, so control, you want to be able to control the experiment by not allowing outside things to invalidate your results. You want to be able to have randomization, in other words, so that you yourself are not causing invalid results by your biasness. You want there to be randomness to what you're doing, especially in a survey, a sample group, and you want to be able to replicate that experiment so that you can confirm or the opposite of that with an experiment. You can confirm whether or not the experiment was valid or not. Experimental results can be ruined by a variety of factors. Being able to control these influential factors is important. One such factor is a confounding variable. A confounding variable occurs when an experimenter cannot tell the difference between the effects of different factors on the variable. That could be like, let's take our love potion number 9 example. Let's say we give our love potion number 9 to our people, and we say, now go get some dates. But it could be that maybe a confounding variable might be that, well, they think they have this thing that's going to cause them to be able to get a date. So they're going to maybe act different because of that. Maybe they have more confidence. Maybe they aren't as uptight. And so they go and try to get dates, but they're not acting the same as they usually do. So that maybe that helps them either get more dates, or maybe that causes them to get fewer dates. But either way, that is a confounding factor that is not attributable to the treatment that we gave them, which was love potion number 9. Okay, here's the example they give in the book. For instance, to attract more customers, a coffee shop owner experiments by remodeling her shop using bright colors, but at the same time, a mall opens nearby. And so you can't tell if the coffee shop gets more customers because of the remodeling or because the mall was open nearby. Another factor that can affect experimental results is the placebo effect. That's kind of what I just talked about. That occurs when a subject reacts favorably to a placebo when in fact the subject has been given a fake treatment. To help control or minimize the placebo effect, a technique called blinding can be used. Blinding is a technique where the subjects do not know whether they are receiving a treatment or a placebo. In a double-blind experiment, the experimenter himself, the researcher, nor the subjects know whether the subjects are getting a treatment or a placebo. Only some outside organization would know that. The experimenter is informed after all the data have been collected. This type of experimental design is preferred by researchers because it minimizes the placebo effect. It also minimizes the bias that could creep in. Randomization is a process of randomly assigning subjects to different treatment groups. In a completely randomized design, subjects are assigned to different treatment groups through random selection. In some experiments, it may be necessary for the experimenter to use blocks, which are groups of subjects with similar characteristics. A commonly used experimental design is a randomized block design. To use a randomized block design, the experimenter divides the subjects with similar characteristics into blocks, and then within each block, randomly assign subjects to treatment groups. For instance, an experimenter who is testing the effects of a new weight loss drink may first divide the subjects into age categories such as 30 to 39, 40 to 49, and over 50. And then within each age group, randomly assign the subjects to either the experimental group, the treatment group, or the control group. Another type of experiment is called the matched pairs design, where subjects are paired up according to a similarity. One subject in each pair is randomly selected to receive one treatment, while the other receives a different treatment. So twins make good for subjects for matched pairs designs. They don't have to be twins, but that's just one example. Sample size, which is the number of subjects in a study, is an important part of experimental design. To improve validity of experimental results, replication is required. Replication is the repetition of an experiment under the same or similar conditions. For instance, suppose an experimenter designed to test a vaccine against a strain of influenza. In the experiment, 10,000 people are given the vaccine and another 10,000 are given a placebo. Because of the sample size, the effectiveness of the vaccine would most likely be observed because it's such a large sample size. You're getting a lot of data there. But if the subjects in the experiment are not selected so that the two groups are similar, according to age and gender and other characteristics, the results are of less value. So let's analyze these experiments and see if we can decide if they're good or bad, or if they're bad, what can be done to improve them. A company wants to test the effectiveness of a new gum developed to help people quit smoking. Identify a potential problem with the given experimental design and suggest a way to improve it. The company identifies 10 adults who are heavy smokers. 5 of the subjects are given the new gum and the other 5 are given a placebo. After 2 months, the subjects are evaluated, and it is found that the 5 subjects using the new gum have quit smoking. All right. The biggest thing wrong with that is that it's such a small sample size. It's only 5. There's only 5 in the sample. It could be that it's just lucky that, that the 5 subjects using the new gum have quit smoking. Maybe they would have quit smoking anyway because it's only 5 of them. There's a lot of room for error in that. If it had been 10,000 people and all 10,000 had quit smoking, then you have a lot better thing to say there. All right, secondly, the company identifies 1,000 adults who are heavy smokers. That's a lot better sample size. The subjects are divided into blocks according to gender. Females are given the new gum and males are given the placebo. After 2 months, a significant number of the female subjects have quit smoking. But see, your problem there is you have a confounding factor, and that is the gender. You're trying to test the gum, not gender. It could be that the females are just better at quitting smoking than males are. And so the gum wasn't what actually helped. It was just the fact that genders are different. So what you want to do is make the two groups, the control group and the treatment group, make those two groups as similar as possible, and that the only difference is the actual treatment that you're trying to study. Moving on. Sampling techniques. A census is a count or measure of an entire population. Taking a census provides complete information, but it is often costly and extremely difficult to perform. So, a sampling is a count or measure of part of a population, and it is more commonly used in statistical studies. To collect unbiased data, a researcher must ensure that the sample is representative of the population. Appropriate sampling techniques must be used to ensure that inferences about the population are valid. Remember that when a study is done with faulty data, the results are questionable. Even with the best methods of sampling, a sampling error may occur. A sampling error is the difference between the results of a sample and those of the population. When you learn about inferential statistics, you will learn techniques of controlling sampling errors. A random sample is one in which every member of the population has an equal chance of being selected. A simple random sample is a sample in which every possible sample of the same size has the same chance of being selected. One way to collect a random sample is to assign a different number to each member of the population and then use a random number table like the one in Appendix B. Responses, counts, or measures for members of the population whose numbers correspond to those generated using the table would be in the sample. Calculators and computer software programs are used to generate random numbers. Let's look at this example. There are 731 students currently enrolled in a statistics course at your school. You wish to form a sample of 8 students to answer some survey questions. Select the students who will belong to the simple random sample. So if you were using a random number table like this, because there are 731 students, you're going to every 3 numbers is going to be a cutoff. So the first number would be 926. And since there's 731 students, the number 926 is just thrown out. The next number would be 307. So you can skip over to this next 307. So student number 307 will be the first student in the test. Then 824. Again, 824 is going to be thrown out because that's more than 731. But the next one would be 019. So number 19 would be in there. And then 267 would be in there. And so on and so forth until you've got enough in your sample. Another way to do this is with your calculator. Let me show you that. So here is this is an emulator for your TI-84. If we click Math, there's a lot of good things in this Math menu. We're going to click over to Probability. Click over to Probability, and then you have this right here. You can click down to Random Integer. Click Enter. And then you're going to put in, it wants a lower limit. Let's let 1 be the lower limit. Let's let 731 be the upper limit. And then N is like how many do we want in our sample. Let's say we wanted 8 in our sample, which is what this study tip on the side of the textbook over here is telling you to do. Say we wanted 8 in our sample. And then we click Paste. And that gives us 8 different numbers that can be used randomly for this sample. So we click to the right and we see all of our numbers. We click back to the left. Get back to the beginning of the list. Yeah. If you have an older version of the calculator, it's not as user friendly. You just have to know, you would just type in randint and then just put the lower limit first and then a comma, and then the upper limit and then a comma, and then the number that you want in the sample, and then close your parentheses, and then it'll give it to you. All right, moving to the next page. All right. When you choose members of a sample, you should decide whether it is acceptable to have the same population members selected more than once. If it is acceptable, then the sampling process is said to be with replacement. If it is not acceptable, then the sampling process is said to be without replacement. So if you had 10 students, you numbered them 1 to 10, and you drew numbers out of a hat, you drew student number 3. The question is, then, if you wanted to, let's say you were asking him his favorite color, and you asked him, so he said red. And then is it acceptable or not to whether you want to put number 3 back in the hat to have a chance to be picked again, or you just, once they're picked, they're picked. And then you can't be picked again. So here are several different types of samples. The type of sample is very important. Let's talk about some different types. One is a stratified sample. When it is important for the sample to have members from each segment of the population, you should use a stratified sample. Depending on the focus of the study, members of the population are divided into 2 or more subsets called strata that share a similar characteristics such as age, gender, ethnicity, or even political preference. A sample is then randomly selected from each of the strata. Using a stratified sample ensures that each segment of the population is represented. For instance, to collect a stratified sample of the number of people who live in West Ridge County households, you could divide the households into socioeconomic levels and then randomly select households from each level. In using a stratified sample, care must be taken to ensure that all strata are sampled in proportion to their actual percentages of occurrence in the population. For instance, if 40% of the people in West Ridge County belong to the low income group, then it's important that the proportion in the sample also be about 40% as well. As an example I like to give would be, so you can try so hard to be unbiased that you actually make yourself biased by trying so hard to be unbiased. Like, let's say I wanted to design a shampoo for women, and I wanted this shampoo, I wanted to test it out on 4 different hair colors to see if it did good on all 4 types of hair. So I'm going to take 40 women in my sample. I'm going to get 10 blondes, 10 brunettes, 10 redheads, and 10 with black hair. And so I take all of these 40. But the problem with that, if we were in a classroom, this would be much more effective. But I would have said to you if we were in a classroom, I would say, now look around the room. All right, how many redheads do you see in the room? And you would probably see not many at all. There might be like one in a class of 20. And so, but I have made them be 1/4 of my sample. So I have overrepresented redheads in my sample. So by trying so hard to represent everyone, I have actually created a sample that is not representative of the population. So that's just something to keep in mind with this. It's just really important to have an unbiased sample, which means unbiased. The mathematical definition of unbiased is representative of the population you're trying to study. That's it. It is representative of the population. All right, here's another technique, a cluster sample. When the population falls into naturally occurring subgroups, each having similar characteristics, a cluster sample may be the most appropriate. To select a cluster sample, divide the population into groups called clusters and select all the members in one or more, but not all, of the clusters. Examples of clusters could be different sections of the same course or different branches of a bank. For instance, to collect the cluster sample of the number of people who live in West Ridge County households, divide the households into groups according to zip codes, then select all households in one or more but not all zip codes, and count the number of people living in each household. In using a cluster sample, care must be taken to ensure that all clusters have similar characteristics. So it may be that one zip code has is particularly loaded with a certain demographic of people by economics or race or gender or whatever. And so then a cluster sample would not be a good way to do things. So a good example of a cluster sample at a high school that I once was a part of, they had lunches. They had 4 lunches. And each lunch was pretty much had every kind of student in it, from 9th grade to 12th grade, and they were just all different kinds of students at the different lunches. And so you just take one of those lunches, and that's a good representative sample of the whole school. So that's a good example of a cluster that would work well. A systematic sample is a sample in which each member of the population is assigned a number. The members of the population are ordered in some way. A starting number is randomly selected, and then sample members are selected at regular intervals from the starting number. For instance, every 3rd or 5th or 100th member is selected. To collect a systematic sample of the number of people who live in West Ridge County households, you could assign a different number to each household, randomly choose a starting number, and then get every 100th household from there. This would work well, except if there's a regularly occurring pattern in the data, then that type of sample would actually create bias as well. A type of sample that often leads to biased studies, and it is not recommended, is called a convenience sample. A convenience sample consists only of members of the population that are easy to come by. So let's say, let's give the lunch example again. Let's say you only surveyed people who were sitting at your lunch table. That's a convenience sample because they're convenient for you to reach. The problem with that is going to be biased. It's not going to represent the population, because most of the time, a lot of people sitting at your lunch table are going to be people who have something in common with you, and so you're not going to be getting a representative sample. Example 4 here. We're trying to identify the sampling technique used and then discuss potential sources of bias. So number 1, you divide the student population with respect to majors and randomly select and question some students in each major. So you are dividing them by major, which means you're creating a strata. That's a stratified sample. The problem with that, the bias that could happen there, is if you do it by major, let's say you're asking these people, do you like math? And you do it according to major. And you're asking the art majors, or the music majors, or the English majors, or whatever, or the math majors. You're not going to get an unbiased sample, The math majors are mostly going to say yes. The art majors are probably, a lot of them are going to say no. So that would not be a good way to do that, if depending on the survey. Number 2, you assign each student a number and generate random numbers. You then question each student whose number is randomly selected. Since each person in that case has an equal chance of being selected because it's so random, that is a random sample, or a simple random sample. That's good. In fact, that's the best way to do a sample. If the more random you can be with your sample, the better chance you have of the sample being representative of the population. That is the preferred way to do it. Number 3, you select students who are in your biology class. All right, that is going to be a convenience sample. We might also call that a cluster sample because they're in a particular cluster, but it's a convenience cluster sample. And that could be biased because all the biology students may be more familiar with stem cell research or whatever you're talking about there. All right, moving. I think that is the end of section 1.3. So good deal. And in fact, that's the end of chapter 1. So, and I'll see you again when we get to chapter 2 for section 2.1.